Hello, welcome to the sixth lecture on error. So far we've been talking about some relatively simple ideas linked to probability, and we've been talking about how random events and random deviations from what we theorize as a correct measurement creep their way into measurements and provide what we call error, or at least random error. And the other kind of error we've talked about is systematic, and we haven't really gone into depth in that yet. All right, today what I want to talk about is something called propagation of error. So the idea is in a lot of practical measurements, your direct measurements are merely used in calculations. And so the question we have then is, what impact on the calculation does any error have? Let me give you an example that comes straight out of my job when I was a plasma torch engineer. Was we had features that we made in, we would drill these cones into the copper tips of plasma torches and into oxyfuel cutting torches. So all kinds of thermal fluid systems, right? Is you'd have this cone. Now I want to please keep in mind this whole thing might be smaller than 1/8 of an inch in diameter. So this diameter here is not big, right? So down here it might be itty bitty, and I have exaggerated the angle. The total included angle might have only been 10 degrees or something like that. So these are very, very slight cones, but it turns out that that's essential for accelerating fluids to really high velocity, that divergence there. And so this is a small geometry on a part, and you really can't, it's so tiny, and the angle is so slight, we can't really get tools up inside of here to measure it. But it's a critical geometry. In a production floor, an operator needed to be able to take a tool and touch this thing and measure the part. Is this part in spec or not? So we needed a way to somehow get up in there without destroying the part, right? And keep in mind, this is all a cylindrical geometry, so there's a center line here. And so we needed a way to figure that out, right? Well, the method that we wound up using, and we went to a lot of trouble to proof this as an idea that it could work and work well, was you take two measurements. One measurement is you drop a gauge ball. This is a very poor sketch of a ball. Apologies. So gauge ball down in there. And this is a precision ground ball, so you know its geometry quite accurately. Maybe you can get ball bearings and gauge balls down to tenths of thousandths of an inch, right? So the precision on that is very high. And there was also a special tool that we could get in here, and we could measure. So this is the diameter of the ball, let's say. And then we could also get in here and measure the diameter where the cone broke the surface. Call that D naught. And with those two measurements, I'm sorry, and we would also, and finally we would measure how high did this ball stand up above the surface. So knowing the diameter of the cone where the cone broke the surface, and knowing how deep down in the hole the ball sat, we could calculate what is the cone angle of the divergence there, and that this was a method that was easy to implement on the factory floor. Right? You just needed gauge balls, and you only needed a couple of specially made tools to just do this measurement very quickly. And the operators, as it turned out, didn't need a ton of special training. It was actually relatively simple. And so one of the big questions, though, is there's a lot of math, there's a lot of geometry that goes into the calculation here. Is from the raw calculations of this, the raw measurement of this height, which has its own confidence interval, right, its own error associated with it, and the diameter of this here. There were two direct measurements that had to be made, And each of those had their own uncertainties. So the question then that we had to answer was, what is the uncertainty? What is our confidence interval? Another way to put it is, what is the uncertainty of the measurement of this angle? Right? So this is just one example where we might have some measured quantity, I'll call it y, that could be a function of many directly measured quantities. So the idea is you might have to take, I don't know, a dozen direct measurements, and then from that you will calculate something that you care very much about. So in other words, another great example of that would be humidity sensors. So most humidity sensors work, one of the really common ones is capacitance, is you have two plates and you measure the capacitance of the air between them. Well, that capacitance is a strong function of the humidity, but it's also a strong function of the temperature of the air. So what you do is you have a temperature sensor hanging out over here measuring the temperature, and you've got this capacitor over here measuring capacitance of the air, and from the two of them you can calculate the humidity. Well, what's the confidence interval on that calculation? This analysis that we're going to use today is how you figure that out. Okay, so well, this function is arbitrarily complex. It could be really super simple, it could be really nasty and complicated like this with lots of trig functions and weird crap in there. But what we want is, so from, if every single one of these if every single one of these direct measurements has some standard deviation or some variance, what implication does that have on y? And that's the question we need to answer. Well, the first thing I will do is imagine that we've taken our measurements and these are the best understanding we have for the values of y. One way we can answer that question is, what if we deliberately, on purpose, what a jerk, what if we deliberately, the nerve, apply some deviation to all of our measurements, some deltas. And then we could ask the question, well, what impact does that have? For sure, you could go through and laboriously calculate every single one of these and quantify them. That can be done. It's a giant pain, though. Like, even if you're a computer, that's irritating. So there is a much better way to do this. And I know you're all going to be really excited to hear it. It's using, I know you've been just waiting for the opportunity to do this, using a Taylor series expansion. I know you love them, so here we go. So if I do, now this is better than just an ordinary Taylor series expansion. This is using a multi-parameter Taylor series expansion. So I'm going to rewrite the original problem, just so we've got it as a reference. I'll only write two x's. You get the idea. There can be arbitrarily many x's. It doesn't matter how many. There are, let's say, lots of them. Well, we can rewrite that. We can expand that using a series, so a polynomial series here. First, you start so we're going to write the series on the deltas. So in a Taylor series, the first thing you do, the first term is always where the parameter is 0. So when the deltas are 0, plus, all right, and now we're going to get the first order terms. So we take not the derivative, but the partial derivative of f with respect to x1. So that is, we're going to address how much does f change but only due to x1. We'll hold everything else constant and we'll only change x1, and that'll be the linear term for x1. We'll do the same thing for x2. Plus, and basically we'll just do that for every single term. We can do that for the squared terms. We're going to end up throwing these away, so I'm not going to go crazy talking about them, but just as I'm sure you all remember well, this is what you would do for the squared terms, because you paid attention in calculus. Whoops, that should have been 1. Sorry about that. Plus dot dot dot. Yeah. All right. So anyway, we can go nuts. As many terms as you want, you can write them, right? So we're going to assume that these delta x's, these small these changes, these deviations away from x from the nominal measurement. I was a jerk to deliberately tweak the measurements and see what effect that had, but I'm not that big a jerk. So we'll assume that these little deliberate deviations from the measurement that we're applying to test, okay, what happens to the output of this calculation, we'll assume they're small. We'll assume they're not that big. What value does that have for us? That means so basically we go nuts here. If I can remember how to spell minuscule, that's embarrassing. So I was going to say minuscule, but then realized, I can't remember how to spell it, so whatever. Really tiny. So the deltas, basically, the idea is if you have a small number, okay, it's a small number, but then if you square it, it's a really small number, and if you cube it, it's a really small number. So the good news is for this Taylor series is the higher order we go, the less those terms matter. They just vanish. They become irrelevant, and we'll only consider these first terms up here, which is nice. That's beautiful. That's nice and simple. So, oh wait a minute, hang on. But this term looks familiar. That's y all over again. Remember we said that this is y. This is my measured value for y. So they just cancel. Gone. And we're left with my deviation in y. That is this change in y due to these changes in the measurement. Are, or well, is rather, just the dot dot dot. And you can just keep going. So however many input measurements you've got, you just take the partial derivative of your calibration function and sum up the effects, and that's the effect it will have on y. All right, so now we need to get to the business. So that's the change due in y. Now, if I just took the expected value of this whole thing, right? If I treated these deviations as random variables, what if these were errors? My goodness. Well, the expected value of this whole thing is just 0. I don't expect x to deviate. Why would it? I don't expect any of these measurements to deviate from their nominal values. Everything, yeah, I expect everything will behave the way it does, the way I expect, yeah. On the other hand, though, variance we can measure. We can say, so what is we can take the expected value of delta y squared, and this will be the variance in y. Cool, so let's do that. So the variance of delta, or the expected value of delta y squared is, this is fun. So let me actually write out delta y squared. Okay, so I'm gonna have to FOIL this in order to actually evaluate that. When you do that, you will end up with two different types of terms. You'll end up with terms that look like this. Oh, excuse me. We're not ready to say variance yet. Sorry. Sorry. I jumped way ahead of myself. There. So you'll have terms that look like this that are just each of these individual terms squared, but then you will also end up with the terms that cross multiply each other, right? So you'll end up with the the interaction terms. So for example, we will also have a term that looks like this. And there will be two of them. And there will be many more, but for all the other terms that we haven't written here. So there'll be an x1 and an x3 and an x1 and an x4 and yada, 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 yada. And it goes on and on. Dot, dot, dot. All right. The expected value of all that. Well, the good news is my calibration is not at all random. That's just a function. So that doesn't really play into the expected value at all. So I can actually, and I can distribute my expected value across sums. So the good news is I can rewrite this to be, this, as messy as this looks, it actually gets very simple very quickly. And we end up with this. Neat. And there are, of course, other terms for the other, and so on and so forth. This is a very special term. This is something called covariance. So how two variables, the expected value of the multiplication of changes in two random variables, that quantifies how much they vary together. So let me lay out an example for you. So let's say we knew that x1 was increased by +1. So delta x1 is 1. My goodness. Does that have any bearing on x2? Is x2 still on average? Does it still tend to be 0? Or if these two are correlated, knowing that x1 is positive means is x2 now more likely to also be positive? If so, this value will not be 0. If these two are correlated, then the expected value of the multiple of two values will actually have an interesting number. Remember that came up. Remember that this came up when we were doing calibration. We saw the expected value of y times x show up. And that was how we ended up calculating slope. But guess what? If two random variables are uncorrelated, if they're just random, this just goes to 0, which is just marvelous. What it means is no matter what value x1 has, x2 on average will still be 0. And the same thing happens the other way around. No matter what value x2 has, x1 still is on average 0. And so on average, this term should still tend to 0. This leads us to a beautifully simple relationship. Let me rewrite what we've just figured out. That's not a 2, that's a partial derivative. Partial derivative. There we go. All right, so that's what we just figured out. Plus, and there could be more, right? However many variables you got. You write that as many times as you need to. What we've just figured out then is, well, shoot, this was the variance for y. This is the variance in y due only to changes in x1, right? So we said x1 will impact y by this amount, right? The partial derivative of f is asking the question, if I change x1, how much will the y change, right? The partial derivative of f with respect to x2 is asking the question, if I change x2, how much will y change? That's what partial derivatives mean, right? And so each of these terms is asking the question, what is the variance in y due only to x1? What is the variance in y due only to x2? What we find is these variances just add. It's that simple. If you have a bunch of different effects, that is multiple independent sources of randomness. Sorry, that should be squared. When you have a confluence of multiple sources of randomness, you can just add the variances of each. As long as those random sources are uncorrelated, remember that was an assumption we made, then it's this simple, right? The variance in y is merely the sum of the variances due to each of these independent sources. All right, let me give you an example, right? So that's the big complicated derivation. So let's have a simple example. So let's say, imagine you've got a beam and, well, let's give it some thickness. Why not? And imagine I have linear actuators somehow. Or shoot, maybe they're measurements. It really doesn't matter. So imagine I specify A and B in order to command a location C, right? So let's say these are linear actuators, or they could be distance measurements, right? And these are evenly spaced on a beam of length 2L, right? Well, we could reasonably ask, so we want to write C in terms of A and B. If I just use the principle of similar triangles, clearly the ratio of this leg here is to this base, or to this hypotenuse, let's use the hypotenuse, is going to be the same as the ratio of this leg here to this hypotenuse, right? So we can use the principle of similar triangles to figure out C. So that'll be the length A plus now we said, all right, the ratio of, it's going to be 2L over L, right, times B minus A is the length of this right here. So we get this. Or obviously the L's cancel, and we're left with C is just equal to B minus A. Or excuse me, 2B minus A. There we go. That's better. There we go. That makes sense because wherever B is, if I extend A, C should move in a negative direction because it's a lever. So that actually makes perfect sense. Good. So we can reasonably ask if the variance of A, so if we have some uncertainty, let's say one of these is a bearing that's really sloppy and really loose. So we've got a lot of or standard deviation. Let's say we've got a lot of uncertainty in one of them. So maybe 20 thousandths of an inch. And then let's say that's at A, and then let's say at B, we've got a much nicer joint. If it'd still be pretty crappy for a bearing, but let's say there's 5 thousandths of standard deviation there. So there's some randomness, some uncertainty of the location of that joint. What is the, if we wanted to be able to produce a confidence interval for where is this point in space? If this is a robotic arm and I'm performing an operation with it, I want to know how confidently do I know the end here. So we can answer that question. By the way, this relatively simple analysis gives you insight into why robots are designed the way they are. If you do a straightforward kinematic analysis, you can find that, well, tons of different ideas for the layout of robots work in theory on paper. Yes, you can locate this point anywhere you want. But all of a sudden, you notice that if you only have finite knowledge of the points you use the actuators you're using to locate a robotic arm, there are certain modes of operation where you're sloppy as all get out at the end of the robotic arm. And so we have to take that into account when you design the mechanism. When you see that these problems can come up, you've got to take them into account. So here we go. So what we learned up here is if we've got some calibration, which we do, right here, we've got it. Our calibration, let's rewrite it. C is equal to 2B minus A. How do we figure out the standard deviation of C from the standard deviations of A and B? Well, here we go. The answer is we don't do it with standard deviations, we do it with variances. So the variance of C is equal to the partial derivative of C with respect to A squared times the variance of A plus the partial derivative of C with respect to B squared times the variance of B. Not so bad. So variance of C is equal to, well, the partial derivative of C with respect to A is, if you shouted -1 at your computer, you are correct. If you didn't, then, well, why didn't you? You should definitely shout -1 at your computer. It's -1 squared times the variance of A. We said that the standard deviation of A was 20 thousandths of an inch. I'm going to be sloppy and leave my units off. And we're going to do the same thing for B. Now, this partial derivative of C with respect to B. Partial derivative of C with respect to B. Remember, we're going to take a derivative of this, assuming everything that isn't B is constant. So If you shouted 2 at your computer, you are correct. The partial derivative of c with respect to b is 2. And we said that the standard standard deviation on b was 5 thousandths. So 0.005, let's say, squared. Okay. Well, that's fun. Notice that even if the partial derivatives, that is the sensitivity of c with respect to a, is negative, you cannot have a negative contribution of uncertainty. You can't take away uncertainty just by inserting a negative sign somewhere. If that were true, we would do this all over the place. No, it doesn't work that way. Uncertainty is uncertainty is uncertainty. If there's something that factors into my calculation and I don't know its answer and I don't know what it is, you can't undo that. So, and that this squared is what asserts that, right? That's what makes this true in this calculation. So, squared is equal to, now I don't have my calculator ready, so let's see if I can get away without it. So this is 4 times 10, 4 to the negative 4th. And then that's going to be plus 4 times 25 times 10 to the negative 6th, which is going to be 1 times 10 to the negative 4th. Neat. So notice something that happened here. B affects the location of C much more strongly than A does, right? Like A is a 1-to-1 relationship. For every inch I move A, I move B an inch, right? But for every inch I move B, I move C 2 inches, right? That's what this says. And that's physically correct. That's physically intuitive, right? That's the way a lever works. So you would expect that A would contribute, or you would expect that B would contribute to the error far more. Not so, because of the way the variances worked out. As it turns out, yes, B is more important to determining C, but what we see is that because I have such a cruddy joint at A, because the standard deviation there is so high, it contributes way more to the variance in C. So the variance turns out to be, for C, turns out to be 0.0005. Yeah, so that's square root of 5 times 10 to the, so if I wanted to calculate the standard deviation, it would be the square root of 5 times 10 to the negative 2. So that's 2. It's less than 3, more than 2, whatever that is. Here, let me. All right, I'll be unlazy and actually calculate it. Let's see. Yeah, 2.24. That's worth committing to memory. All right, so notice what happened. It is impossible with this relationship. There was no way, because all of these impacted C greater or equal to the partial derivatives are 1 or bigger, right? There's no partial derivative that's less than 1. The sum of the variances it can't possibly be less than any one of the variances. That won't be true anymore once these take on once these take on more interesting values. But in this case, yeah, sure enough, we see more slop in C than we see in any one of the contributing joints, right? So that's the game. Is you can never take away uncertainty. You can only add to it. Oh dear. And that's how it works. All right. Well, thanks for watching. I'll have examples up.